Assalamualaikum warahmatullahi wabarakatuh. Hello everyone, specifically this is an all participant International WALISONGO Science Competition 2026. Let me introduce myself. My name is Muhammad Kholil Fauzan, and I am physics student at UIN Walisong Semarang, Faculty of Science and Technology. Today I will explain our mechanical system. This system consists of a hook, a spring, a recruit, a rope, and appointments. In this presentation, I will explain the system, how it works, the constraints, the degree of freedom, and the equation of motion. Let's start with structure of the system. At the very top, there is a hook attached to the can. Its job is to hold the entry system. Below the hook, there is a spring. The spring is a most important component because it can strengthen and compress. When it changes its length, it creates a restoring force that always there's to bring the system back its original position. Next, we have the recruit. Unlike the spring, the rod cannot stretch or bend. It simply transfers the force from the spring to the lower component. The rod is connected to a rope. We assume the rope has no mass and cannot stretch, so it only transfers force. Finally, at the bottom, there is a point mass. This is the only part of the system that moves, so it is the object we analyze. Now, let's see how the system works. At first, the system is in equilibrium. This means the downward gravitational force is balanced by upward spring force. Now imagine we pull the mass downward as the mass moves down. The spring strengthens and stores electric potential energy. When we release the mass, the spring immediately pulls it upward. But the mass has inertia, so it keeps moving upward even after passing the equilibrium position. After reaching an highest point, gravity pulls it downward again. The same process repeats over and over, so the mass moves up and down continuously. This repeat motion is called simple harmonic motion. During the motion, energy is constantly changing. At the lowest point, most of the energy is stored in the spring. Near the equilibrium position, most of energy becomes kinetic energy because the mass moves faster. At the highest point, the kinetic energy decreases again, and gravitational potential energy becomes stronger. This continuous energy conversion is what keeps the oscillation going. Now, let's discuss the constraints. The constraints is something that limits the movement of the system. In the system, there are two constraints. The first constraint is the recruit because its length never changes. The second constraint is the rope because it's assumed to be inextinguishable. Because the test constraints, the mass cannot move freely in every direction. It can only move up and down. Next is the degree of freedom. The degree of freedom tells us how many dependent movements the system has. Since the mass only moves vertically, we only need one variable x to describe its position. Therefore, the system has one degree of freedom. Finally, I will explain how we get the equation of motion of the system. The first step is to identify the force acting on the mass. Since the rod and the rope are assumed to be right masses, they only transfer force. Therefore, we only need to consider the force acting on the mass. There are two forces acting on the mass. The first force is the gravitational force, or weight. Gravity always pulls the mass downward, and its magnitude is Fg equals mg, where m is the mass and g is acceleration due to gravity. The second force is the spring force. When the mass moves downward, the spring strengthens. The more the spring strengthens, the layer of force it produces to pull the mass back upward. According to Hooke's law, Fs equals k times x, where k is the spring constant and x the displacement of the spring. Notice that the spring force always acts in the opposite direction of the displacement. This is why the spring is called a restoring force, because it always turns it return the system to its equilibrium position. Now we apply Newton's second law, which is stated that sigma F equals mx double dot. This means the total force acting the object is equal to its mass multiplied by its acceleration. For analysis, we chose the downward direction as positive. Why? Because the mass mainly moves downward when we strengthen the spring, making this change easier to understand. With this convention, gravity acts downward, so it is positive. The spring force acts upward, so it is negative. Therefore, the total force becomes mg minus kx equals m times x double dot. This equation tells us the acceleration of the mass depends on the difference between gravity and the restoring force of the spring. Next, we rearrange the equation by moving the spring force to the other side. M times x double dot plus k times x equals m times g. This equation describes the motion of the mass measured from the natural leg of the spring. However, engineers usually analyze vibration from the equilibrium position because it is much simpler. At equilibrium, the spring force exactly balances the weight of the mass. So, mg equals k times x0, where x0 is the spring attention at equilibrium. If we define a new displacement, y equals x minus x0, meaning that y is measured from the equilibrium position, then the constantly gravity term disappears. The equation becomes my double dot plus ky equals 0. This is called the simple harmonic motion equation. From the equation, we can understand that whenever the mass moves away from the equilibrium position, the spring always produces a restoring force that pulls it back. Because the mass has inertia, it overshoots the equilibrium point, and the same process repeats. That is why the mass continues moving up and down in an oscillatory motion. Thank you for attention and thank you for watching. Bye bye. Assalamualaikum warahmatullahi wabarakatuh.